But I kind of regret it now because that's so much free time. Is it a homework or you have to do it?
All right,
Okay,
it's 9:40, so let's get started. So, welcome to the second week. Quiz 1 solutions are posted, so if you either didn't do as well as you wanted on the quiz or didn't actually do the quiz, solutions are posted on the website. I also posted solutions to all the exercises we did last week. If you were here or if you weren't here, then those will actually be really helpful in the exercises that we did last week. Homework 1 is also out. Remember that although it is optional, it's highly recommended that we do the exercises. And I think the first part is due this Sunday or Saturday at midnight, so make sure to do that. Any other questions before we get started? Yeah.
Wait, so homework is separated into 2 parts, right?
Yeah.
So the first part's due up.
Yeah, the first part's due, I think either Saturday or Sunday at midnight, and then the next part's due the week after. Yep. Any other questions before we start? So the way that these work, if you weren't here last week, is we're going to go over some exercises that are on the sheet here. On the back are 3 additional exercises that, if we have time, we may touch on. But if we don't have time, then I'll leave it as an exercise for you to do. They're not for credit, but it's just for some extra practice that may be helpful with some of the materials. Any other questions before we start? Okay. So what was the major thing we talked about last week? Yeah.
Constructing a DFA.
Constructing a
Formal definition and constructing
DFA, right?
Yeah.
Yeah, so a DFA, but what else did we talk about with in terms of DFAs? Well, the formal definition, but what else did we do with DFAs?
Read input.
Well, we read input, but how do I combine DFA's languages together?
Formal definition.
Well, it's not the formal definition.
compare them.
Well, not necessarily compare them, but how do what is a language? How about that? What is the definition of a language?
It's the set of all strings that a DFA accepts.
Yes, it's the set of all strings that the DFA accepts. So what do I want to do with strings? With languages. What is the first thing I would want to do with a set of strings? Yeah, union, right. So we would want to do a union operation. What's another one that we might want to do? Intersection, yeah. What's the third one that we might want to do? Complement. So I'll ask again. What was the major thing that we did last week? Is to to show that DFAs are closed under, well, the regular languages are closed under union. Remember that we can take 2 regular languages, form their union, and that we found was to be a regular language. So how did we actually do that? Well, here's an idea that won't work. Whatever string I have, feed it into the first DFA and see if it accepts. If it does, then it's always going to be in the union, so we're done. If it's not in that, if the DFA does not accept that string, then we feed it to the second DFA and see if it accepts. If it does, then it's in the union. If not, then it's not in the union. So what's the problem with that idea?
You can't rewind the input.
I can't rewind it. So what was the strategy that we came up with?
Run them in parallel.
Run them in quote unquote parallel. So how did we make a DFA to run in parallel?
We created a new DFA using those strings.
Yeah, we made a new DFA, right? So if we have DFAs M1 with states Q1, sigma, delta 1, start state Q01, F1, and M2 is Q2, sigma, delta 2, Q02, and F2. So we made a machine M, and what were the states of this machine?
Q1 cross.
Yeah, Q1 cross Q2. And so why is that? Why would I want to have this? Because what I'm thinking is, I'm gonna keep track of what state I would have been in the first machine, in the first coordinate of the ordered pair here, and where I would have been in the second machine here. And so that's exactly what we want to do. Sigma is still going to be the alphabet. I'll define the delta in a second. So what would the start state of this machine be? Right, it has to be an ordered pair because all the states are ordered pairs. That's non-controversial. But I want it to be an ordered pair, but I want it to be the original start states of both machines, right? So that's what I want there, and then I'll define F in a second. All right, so let's figure out what delta is. Well, remember, what does the transition function take as input? State and an input character. Well, since all these states are ordered pairs, the first coordinate has to be an ordered pair. So I'm going to say that the ordered pair is Q1, Q2, and the symbol is A. So what is the transition function output? What does it give back to me? A new state, right? I'm in a state, I read a character, I go to another state. But all the states are ordered pairs. So I have to go to some ordered pair. But how do I figure out which ordered pair I go to?
Run on individual machines.
Yeah. So the first coordinate has to be a state from the original first machine. But how do I figure out where I would have gone in the first machine? Well, this first coordinate says, I'm in state Q1 right now of the first machine. And I read a symbol A. Well, how do I figure out where I go in the first machine? The transition function of the first machine, right? That tells me where it would have gone. So I follow the transition function of the first machine with the corresponding state. And so what is the second coordinate then?
Delta 2. So
Delta 2, yeah, with Q2. So delta 2 with Q2A. Good so far? All right, so then what's F? Oh, note one thing. Everything I've defined so far, is that specific to union? Is that specific to intersection? No. So the only thing that's going to matter here are the final states. So let's just say we're doing union now. What would the final states be?
Ordered pair of all final states in the group.
Right. So I have to have ordered pairs first of all. No controversy there. Well, how do I determine if it's in the union? Well, that must mean that either one of these or both is a final state, right? It doesn't have to be the case that both of them are final. At least one of them has to be final. So Q1 is in, well, how do I determine that, say Q1's a final state?
Q1 belongs to
I gotta check if Q1 is in the final states of the machine it was from. So Q1 is in F1, or Q2 is in F2, or both. So that's not an exclusive form. So this is for union. How would I do the intersection? So what would I have to change about the final states to work with intersection instead of union?
change the OR to an AND.
Right, change the OR to an AND because I have to have both of them be a final states of the original two machines. Okay? So that takes care of union and intersection. How do I do complement?
does not belong to the final state.
So let's just say I have some DFAs, say M1. How do I find the complement DFA, or the DFA that accepts the complement of M1's language? Whatever that is.
Reverse the final states?
Yeah, reverse the final state. So I flip whatever was final before to be final now, and whatever was final before to be non-final now. So I just swap the final and non-final states. And so that one's pretty easy, and the other ones are just combining two DFAs and then figuring out where each DFA goes. Okay? Any questions about any of that? This is the time to ask questions, seriously. Okay, so let's actually do some of the exercises on here. So the first one says that I want all strings W in 0, 1 star. And so the notation here means the number of occurrences of the character in the subscript, which happens to be 0 here, the number of occurrences of that character in W is not equal to 2. All right, so I want all the strings that have either 0 zeros, 1 0, or 3 or more zeros. I don't want any with exactly 2. Okay? Everyone got the goal I'm trying to do? So let's figure out how I would actually do this. So what's a good strategy once you see this? What's your initial gut reaction I should try to do here?
Count the number of zeros.
Well, I could count the number of zeros, but how would I try to make this as easy as I can for me?
So I create 3 states from which has true transitions, like 0 to 0. So the third one will not be a final state. So if it's going to that, it shouldn't be the same.
Yeah, I could do that, but do you see something that can make this easier? Because I need to think, well, if I don't have 1 0, then where do I go on 0 and where do I go on 1? It just seems more complicated. I could do complement. So what is the complement of this language? Yeah, just equals to, right? So I think checking whether something is equal to something is much easier than checking whether it's not equal to something. That seems a little easier for me. And then, could I make a DFA for the complement? Am I allowed to do that? Yeah, and then at the end, what do?
Change the final.
I change the final states because that's how we show closure under complement. So let's think about L bar. So if this is L, let's think about L bar, which is the exact same thing, but the number of zeros is equal to. And we'll go with the suggestion from earlier. Let's try to count the number of zeros. Well, if I have a start state, say Q0, how many zeros have I seen so far? 0, right. If I read a 0, then how many zeros have I seen? 1. So what do you think would be a good name for the next state? Q1, right. So the names, remember, don't mean anything, but it's just helpful for us to remember that the subscript represents how many zeros I've seen so far. So here I've seen 0, here I've seen 1. So what do I do here? If I've seen 1 0 and I read another 0, how many have I seen? 2, right. So let's just have a state with Q2. So should I accept on this state? I better accept the string 0, 0. I better accept that string. So I better make this an accept state. But let's think. If I read a 0 here, what happens? Okay. Should I loop on 0 here? No, right, because I don't want to accept anything other than 2 zeros. So what should I do here if I see a 0?
Go back to any other state.
I should go to another state. So what should that state I'm going to do? If I've seen 3 zeros, do I care what the rest of the string is? No. Should I ever accept at that point if I've seen 3 zeros? No. So if I see another 0, say Q3, what should this state do on any input at all? I remain in that state. Good. So 0, 1. Am I done? What if I forgot? The 1 transition. Okay. So what do you think Q0 say is going to do on the input 1? It should stay there. Why? Because if I see a 1, then that doesn't change the number of zeros I've seen. So I should remain here on input 1. What do you think these two states are going to do on input 1 then? They're going to do a self loop also. So we're all gonna do something. Okay? So now, what is this DFA a language for? It's language.
Any string which has
Which of these two is it a language for? L bar, right? And I wanted one for L. So what do I do to fix that? I've changed the final and non-final states. Good. So what is this state going to be? Final or non-final? Yep, it's going to be final because it was non-final before. Final or non-final? Final, good. Final or non-final? Non-final, right? Because it was final before, so I'm going to erase the double circle. Final or non-final? Final, good. All right, so to me, it's much easier to think about something where I only have to check equality with one thing versus checking equality with infinitely many things. Although with the suggestion before, we could have come up with that, but to me, it's just a lot easier to think, okay, I need only check this one case. Okay? Are we good with that? Yeah.
how can we know whether the DFA we have created, there is no one which is like shorter than that this is one DFA for this language. We can also have another DFA for the same language.
Yep.
So how can we know whether which one will be the shortest?
We're not primarily concerned with how many states the DFA has. We're just concerned, can we make it? The question of what is called DFA minimization is very interesting, but we're not going to cover that here. Yeah. And this actually, you can prove is the minimal DFA for this. You can't have any with three states. Any other questions? Okay, so let's do this one. So it says, I want all the strings in 0, 1 star such that the number of occurrences of 0 is even, and the number of ones in the string is either exactly 1 or exactly 2. Okay? So the number 1's part kind of relates to the one up here, but we haven't seen this one yet. And we have this word and in between, so it's going to venture into somewhat new territory here. So when you see this word and, what do you think in your head?
Intersection.
Intersection, right? Because I want that condition to be true and this condition to be true. So let's think about it. If I have a language, say L1 for this first part, and a language L2 for this part, it seems like this one is the intersection of those two languages. So if I can make a DFA for this part and a DFA for this part, can I make a DFA for the whole thing? Yeah, because we talked about intersection and we can clearly do it. So let's make a DFA for both. So let's make a DFA for, I'm going to call it L1. So it's the same thing, but only the first condition. So the number of zeros is even. So any suggestions on how I can make a DFA for this one? So this goes back to one of the strategies I talked about last week. How many possibilities are the number of zeros in W? In terms of being even or odd, or can it be anything else? No, I don't think so, because it can only be even or odd. So one strategy is to make each one of those possibilities a state. So let's make a state called Q even, which represents, we've seen an even number of zeros, and one for odd, we've seen an odd number of zeros. So let's do that. Q even, Q odd. And then let's just figure out what this DFA does. First off, what should be the start state?
Q even.
Q even, why? Because when I've not read any characters, how many zeros have I seen? 0, and that's an even number. So Q even needs to be the start state. What should be the final state or states? Q even, because I want to recognize the is even condition. Good. So I want that to be final state. Then now I got to figure out where the transitions go. So where should Q even go on 0? Q odd. Why? Because if I've seen even number of zeros, if I read one more, now I've seen an odd number, whatever that number is. So I should go to Q odd on 0. But where should I go on 1? I should loop, because as we talked about up here, if I read a 1, that doesn't change the number of zeros that I've seen. So this should self-loop on 1. What should Q odd do on 0? I go back to Q even for the same reason. If we've seen an odd number of zeros and we read one more, then we've seen an even number. Q odd on 1, what do you think that does? It does a self-loop again because it doesn't change the number of zeros that it's seen. Good. Any questions on that part? Okay. So I clearly will need more room. So let's now make a DFA for the second condition. So that's going to be L2, I'm going to call it. So it's the same thing, but the number of ones in W is exactly 1 or exactly 2. Okay? So how do you think I can go about making a DFA for this? Do we have any prior knowledge of a DFA that will help us? Oh yeah, this one, right? It has the number of zeros is equal to 2, but could I interchange the zeros and ones to make, that would make a DFA for the number of ones is equal to 2. So, but that was the complemented one. So this was the only final state for the one that we want to recognize. So let's make a DFA for exactly that. Q2, Q3. Again, Q3 is going to loop on everything. And now these transitions, instead of being labeled with 0, I interchange them, so I want them to be labeled with 1. So these are going to be labeled with 1. And the self loops now, instead of being labeled with 1, are going to be labeled with 0. 0. But now I got to figure out what the final states are of this machine, right? So what are the final states of this machine? Yeah, so before I had exactly 2, and we had the Q2 state being the only one final. So here I want exactly 1 or 2. So that should mean Q1 and Q2 are the accept states. So I'm going to make these two the accept states. We good so far? So now I gotta do the product construction on these two DFAs to make one for the intersection. So first off, how many states is this machine gonna have? So this one had 2, this one had 4. It would have 8, right? Because I gotta make an ordered pair with this as the first coordinate and each one of the other ones as the second one. This one as the first, and all of those in the second coordinate. So I gotta make 8 states. So the notation that I commonly use is I'm gonna put 2 subscripts, and the first one is gonna come from this machine, so it's gonna have an even or odd on it, and the second one will come from that machine, so it'll say 0, 1, 2, or 3. So I'm gonna make a state Q even, and I put a comma for convenience. Even 0, Q even 1, Q even 2, Q even 3. And then now the odd ones. Q odd 0, Q odd 1, Q odd 2, and Q odd 3. Okay? Good so far? All right. What's the start state of this machine? Let's try to figure that out. What's the start state of the machine? Q even 0, right? Because I gotta look up the start state of the first machine and the start state of the second machine. And whichever state in the machine I make corresponds to both of those, that's the start state. So this one is gonna be the start state. So I'm gonna avoid doing the final states for now. I'm gonna do those at the end. So now we gotta do the transitions between the states. So let's figure out, if we're in Q even 0, what do I do on input 0? Yeah, so let's think about it. If I'm in Q even, that must mean I was in Q even over here. Where does this machine go on input 0? It went to Q odd. So I'm thinking in my head, Q odd, that's where I'm gonna go. Now I gotta think, in this machine, where do I go on 0? Well, I go back to Q 0. So I think odd 0. Well, do I have that state? I sure do. So now this comes down here on input 0. Where does Q even 0 go on 1?
Q even 1.
Q even 1, let's think about it. Q even on 1 stays in Q even. Q 0 on 1 goes to Q 1. So I think even 1. Oh, I have that state. So I'm going to make a transition here. Let's think, Q odd 0. Where's that going to go on 0? Well, it's going to go to Q even, so I'm thinking even. Where is Q 0 going on 0? Well, again, it goes back to itself on 0. So I think even 0. Oh, I have that state. So it comes back here. Does this tell you anything about what the 0 transitions are going to do? Well, think about it. Where do the 0 transitions go on any state in this machine? They're self-loop, right? So wherever the 0 is in any of these states, it's going to either remain here or go to here, or the other way around. Where do the 0 states come in here? Well, whatever state I'm in, it goes to the other state. So what do you think the 0 transitions are going to do for the other 6 states? They're going to go up and down, right? Because they must stay in the same column, but they're not going to self-loop, because if you were in even and you read a 0, you go down. If you were in odd and you read a 0, you go up. So all the 0 transitions are going to cross like this. And so it's really nice when you make DFAs like this to see symmetries like this. Every state loops on 0 in this machine. Every state goes to the other state in this machine. Okay? So that was really nice that we were able to get all the 0 transitions in one step. In general, we should do this per state, but we were able to see the pattern here, which is nice. All right, so let's do the 1 transitions. Q odd on 0, Q odd 0, where does that go on input 1? Well, let's think. Q odd is going to stay there. Q odd 0, that's going to go to 1, so I'm thinking odd 1, and that's the same. What do you think the other states are going to do on input 1? We can actually see another symmetry here. What do the states here do on input 1? They stay in the same state. So no matter what state I'm in this machine, I'm going to stay in the same row. So they can only either go to another state in the same row or loop on themselves. But here, what do? Well, Q0 is always going to go to Q1, so that's why we had these 2 transitions. What do you think Q1 is going to do on input 1? It goes to Q2. So what do you think these 2 states are going to do on input 1? They're going to go right 1, right? Because they got to stay in the same row and go over 1. So that's what we have. think the two states are going to do on input 1? They're going to go to 3, but for the same reason, because Q2 always goes to Q3 on input 1. And so now here's the kicker. What do the 3 states do? They must self-loop, right? Because there's no fourth state to go to. And they must self-loop because they self-looped here and they self-looped here. All right? Am I done? Oh yeah, final states. Does this DFA accept anything as is?
No.
No. So it clearly is not an intersection yet. So I'm doing intersection, remember. So what states are going to be final of this machine? Yeah, so it has to be in the even one because the odd is not final. But it also has to be either Q1 or Q2. So I'm thinking even 1 and also even 2. So even 1 is going to be final, and even 2 is going to be final as well. All right. Was that pretty simple? Is there any confusion about any of that? Okay, good. So let's do the next one. So we're good over here on the left side? No responses, so I'm assuming. All right, so the problem is W in 0, 1 star such that number of zeros in W is even, or number of ones in W is not a multiple of 3. Okay, so that's the problem I want to solve. What is your initial gut reaction when you see this? What is the first word that you see that is really important? Or, right? Or instead of and before. Oh, what does that tell you about this? It's going to be union. So anytime you see and, think intersection. Anytime you see or, think union. Well, can I make a DFA for this first part? Can I make a DFA for the number of zeros is even?
Yes.
Yeah, how do you know that? Yeah, I already did that. So let's put that up here because I don't want to forget. All right, so that's the DFA that we had before. So now all we have to do is make a DFA for this second part. For the number of ones is not a multiple of 3. So what in that second part stands out to you? Not, right? Oh, what does that initially tell you we should do? Complement. So let's do L2 bar. So I'm going to call that part L2, and I want the complement. So this is the same thing. I want all the strings in 0, 1 star. So that the number of ones in W is a multiple of 3. So that's what I want. So can I make that? So when you think multiple of 3, so what was the examples that we've seen in class and recitation initially tell you we should do? Well, you may think, well, is a multiple is not a multiple of 3, and then just make those two as states. But the problem is, how do I relate the not a multiple of 3 together? So what should I do instead? Remainder, yeah. So how many remainders when corresponding to 3 are there? 3, 0, 1, and 2. So let's make a state for each one of those. So I'm going to call them Q0, Q1, Q2. What's the start state of this machine? 0, right? If I've read 0 characters, that must mean that the number of ones that I've seen is 0, which is a multiple of 3. So Q0 better be the start state. What is the final state or final states of this machine? It's only Q0 because I want exactly remainder 0. All right? So let's do the transitions. Q0 on 0, where does that go? It's going to loop on that because if I've seen a multiple of 3 number of 1s, if I've seen a 0, that doesn't change the number of 1s that I've seen. So this is going to self-loop on 0. Oh, what does that tell you about the other 2 states on 0? Same thing, because it doesn't change the number of 1s that I've seen. So these 2 states are again going to loop on 0. And so now the interesting thing is, what does it do on input 1? So what does Q0 do on input 1? Goes to Q1. If I've seen a multiple of 3 number of 1s and I read 1 more, now the remainder is 1. So I better go to Q1 there. What do you think Q1's going to do on input 1? It's going to go to Q2 for the same reason. And what do you think Q2 is going to do on input 1? It's going to go back to Q0, right? Because, well, wait, wouldn't it go to Q3? Shouldn't it go to a state Q3? Oh, if you just add 3 to a number that's already a multiple of 3, the new number is now still a multiple of 3. So it should go back to Q0. Okay, now I want a DFA for the original one. So what do? I do complement of this DFA. So if I wanted, instead of bar, and I wanted not here, what do I do to this DFA? Switch the final and non-final states. Good. So make this not final, make this guy final, make this guy final. Good with that? So now let's make the product DFA for this. All right. So how many states is this DFA going to have? 6, because I had 2 up here and 3 down here. So I'm going to have 6 states. So I'm going to call them in the same convention that I did there. Q even 0, Q even 1, Q even 2. Q odd 0, Q odd 1, Q odd 2.
My question, so if you're in Q1 state, that means the remainder is 1, right?
Yeah.
So if you receive a 0 after that, won't you go to Q2 instead?
The number of 1s is a multiple, not the number itself. Yeah, so it's quite different. You're right. If I'm thinking about the binary number itself as being multiple 3, you would be right in that case. But I'm thinking about the number of 1s, which is different. Any other questions? Okay. So let's think, what would the start state of this machine be? Well, it better be Q even with Q0, like we did before. It's got to be the start state of both machines. So this has better be the start state. Let's do, again, final states at the end. So let's do the transitions. Q even 0 on input 0. Where would that go? Well, let's think. Where does this machine go from Q even on 0? Goes to odd, so I better go one of the 3 states on the bottom. Where does this state go on input 0. Itself. So this one also goes down to Q odd, like the example from before. Let's think, maybe we have the same pattern we had before. What does Q odd 0 do on input 0? Well, where does Q odd go on 0? Back to Q even, so it's one of the top three. What does 0 do on 0? It goes back to even. So what do you think the other states are going to do on input 0? Well, let's think about it. If you're an even, you're always going to go to odd. If you're an odd, you always go to even. So if I'm in the top row, I always go to the bottom row somewhere. In this DFA, where do I go on input 0? I do a self loop, right? So whatever state I'm in here, I'm going to stay in the same column. But I'm going to always go to the other row. So I really do have the same behavior as before. So I do have all the 0 transitions crossing the gap. All right? Even though we've had a completely different language, we still have the same behavior with the 0 part. All right, so now we just got to fill in all the 1 transitions. So what does Q even 0 do on input 1? Well, Q even on 1 goes where? It goes to Q even as a self loop on 1. So I'm going to be in the top row. Where does Q0 go on input 1? It goes to Q1, right? So I got to think even 1. So I better go to state even 1 there. Okay? What does Q odd 0 do on input 1? Well, odd, where does it go on 1? It self loops. What does Q odd 0 do on input 1? So 0 goes to 1 again. So what state am I going to go to next? Even 2, definitely. Really, what state am I going to go to? Well, I better stay in the same row because I self-looped on odd, so I'm going to be in an odd state. But I'm in 0 now, so where does 0 go on 1?
Q odd 1.
Q1, yeah, so I better go to odd 1. It's the same condition as before, but now with odd. What do you think Q even 1's going to do on input 1? It's going to go to Q even 2, right? Because even stays at 1, 1 goes to 2. So it's going to go over here. What do you think odd 1 is going to do on input 1? Well, odd stays there. 1 again goes to 2. So I better go to odd 2 again. Now is where it gets interesting. Where does even 2 go on input 1? Even 0, right? Because even better stay in the top row. 2 goes back to 0. So even 2 will come back to even 0. Let's see if I can label this. Where does odd 2 go on input 1? It goes back to odd 0. Why? Odd stays there on 1. 2 again goes back to 0. So odd 2 is going to come back. And that's what happens. Am I done? No, what have I forgotten?
Final states.
Final states. Oh, okay. So what are going to be the final states of this guy? So there are 2 ways you can think about it. Every state that has even in it, make it final. Every state that has 1 in it, make it final. Every state that has 2 in it, make it final. Or you can think about it the other way. Any state that has odd and 0 in it, make that not final. And make all the other ones final. So every state but odd 0 is going to be final. So this one's final. You're final. You're final. You're final. suppose that I just messed up and I completely wrote the wrong language, and I meant this. I meant to write and, but I wrote or instead. What would I have to change? Do I need to do this whole thing again? No, what would I have to change? Final states. Okay, so if I were to write and there, what would the final states be? Even 1 and even 2. Yeah, so those two would be the only final states in that case. What did that take, like 20 seconds? And the other one took like 10 minutes. So the important point in here is that union and intersection in this case are related to each other. You only have to change the final states. That's the only thing that changes. Okay? Any questions about any of that? Can you do the last? We can try starting the last one, although it might run us over time. 4 minutes, okay. So let's just start doing the last one. So this one is slightly different, but it makes you think about union and intersection a little bit more. So I want all the strings in 0, 1 star, such that the number of zeros in W is exactly 2, or the number of ones in W is exactly 1, but not both. So it isn't it's not intersection or union anymore, right? It's because of this but not both part, right? So let's just say that I really did mean to write or here, but I forgot to write but not both in here. So how would the final states of this DFA change? Right, so the ones that are the intersection states, the ones in the first mistake that I did, convert those to be non-final now. So what ones am I going to make non-final now? Even 1 and even 2. So this one is not final, this one is not final. All right, so we can think about this as doing union, but taking out the intersection states. So we phrased it in terms of both union and intersection, although we only have to do the operation once. Okay? So can I do a DFA for the number of zeros in W is exactly 2? Can I do that? Yeah, we already did that. And so here's the DFA that we did. It helps to actually have the DFA here. So this is the DFA that we had. And I have the one for, so, yeah, I'm going to do it that way. So I'm going to write this DFA vertically for a reason you'll see in a second. So L2 is same thing, but the number of ones is exactly 1. We didn't actually do a DFA for that, but can you make a DFA for that? Yeah, so how would I change that? What would I have to do? Okay, well this one seems very related to that one. So maybe I can just make a copy over there, make this state final, this one not final, and then just move this over, right? Instead of having a path of length 3 here, I just have 1 and 2, because I only want I want to recognize exactly one. So let's have 3 states. I'm going to call them A, B, C, because I don't want to confuse it with those 3 states. B, B, C. So this is my start state. This is going to go to here on 1. So remember, I'm looking at the number of ones now. And then here we do a 0, 1, 0, 0. And then this is final. So this DFA is very related to this one. I only had to change one state out of it. Actually, I could have just removed that state, interchange the zeros and ones. All right? So why do you think I wrote it this way? Horizontal then vertical. So I can think about this particular row as being in QA, and this one as being in Q0. So this is all a very common way of writing the product DFA. So I can think here as being QA, and this column being Q0. So that's a very common way to do it. So QA1, QA2, QA3, QB0, QB1, QB2, QC0, QC1, QC2, QC3. So we won't have enough time to do all the transitions, but what's the start state of this machine? So it's going to be the start state of this machine, which is QA, and start state of this machine, which is 0, so that one's the start state. So you can fill in the transitions, it's not very difficult. But let's try to think about what the final states are of this machine. So what do you think are the final states? Well, we thought of this as doing union, but then afterward taking the intersection final states out. So what would the union be here? Right, so anything that has B in it would be final because B was the final state. So this one's final, that's final, that's final. Any other states that are final? Right, the ones that have Q2 in them. So this one's final. We already marked that one. This one's final. So now what do? I want to take the intersection states out. So what are the intersection states? The ones that have a Q2 and QB in them. Oh, I have QB2 right there. So I'm going to make this guy not final. Because I don't want both of them to happen at the same time. Okay? Any questions about any of that? So I encourage you to work on the 3 exercises on the back, and I'll see you next week.